Welcome back to The Explainer. Today, we're looking at a fascinating breakdown by Masgray, diving deep into the microscopic mechanics of C++ code execution. We're going to see how one of the most basic operations in programming is secretly hiding some major baggage, and how compiler engineers are literally rethinking memory management to squeeze out every single drop of performance.
So think about this. Why does adding just one single item to a container potentially slow down your entire program? It sounds like the easiest thing in the world, right? You've got a list, you tack an item onto the end, and you move on. But beneath that simple action is a massive, completely overlooked bottleneck. When your code is firing millions of times a second, those tiny hidden instructions the compiler tacks on to prepare for the worst-case scenario, they act like a parachute dragging behind a sports car.
Okay, let's dive into Chapter 1, the Container Performance Bottleneck.
To really get this, we need to look at LLVM. It's the compiler infrastructure powering a huge chunk of modern software. Its go-to container is called small vector, and its absolute hottest operation is pushback. That's the command you use to add an element to the end of the vector. Now here's the golden rule of container optimization. The fast path has to be lightning fast. What's the fast path? Well, when you add an item, the vector checks if it has enough pre-allocated capacity. If it does, boom, it just drops the item right in. That's the fast path. If it's out of space, it hits the slow path and has to allocate new memory. For peak performance, that fast path needs to execute with literally zero friction.
It's basically like packing for a trip. The fast path is like tossing a new shirt into an open, empty suitcase. It takes, what, a second? But the slow path? That's realizing your suitcase is totally stuffed. You literally have to stop, drive to the store, buy a bigger bag, drive back, empty the old bag into the new one, and then you can finally pack that one shirt. In code, that slow path means calling some pretty heavy memory allocation functions. Our goal here is to make sure tossing that shirt into an empty bag isn't penalized just because the bag might be full.
Which brings us to Chapter 2, the shrink wrap problem.
Compilers, can be a bit overly cautious. And that introduces the unexpected villain of our story, the stack frame. See, the compiler actually wastes time saving registers on the fast path, just to prepare for the slow path. When it turns pushback into machine code, it sees that buying that new bag requires external function calls. So to keep its current data safe, it pushes it all onto the stack, creating a stack frame. But here is the kicker. It sets up this heavy safety net on the fast path. Every single time you toss a shirt into the bag, the compiler is essentially laying down a tarp and strapping on safety goggles just in case it has to run to the store. You end up with 14 instructions instead of a clean, minimal execution, and standard optimization tricks like shrink wrapping totally fail to fix this.
So how do we fix it? Chapter 3, the tail call solution.
Masgray outlines this absolutely brilliant compiler-level breakthrough for LLVM. It's all about tricking the compiler into letting that fast path run completely free. Step 1. We take all that heavy, slow path logic for growing the vector and move it out of line. We basically quarantine it into a separate helper function. Step 2. We tail call it. We set it up so that if the vector is full, calling that helper function is the absolute final thing the pushback operation does. And step 3. Because it's a tail call, the fast path doesn't have to save its state to return later. It is finally free from the baggage of saving registers and runs entirely unencumbered.
Let's look at the impact in Chapter 4, Real-World Results and Standard Libraries.
Theory is great and all, but the actual results are wild. By using this tail call trick in LLVM's small vector, that fast path dropped from 14 instructions down to just 7, no saved registers, no stack frame. When they applied this to LLD, the LLVM linker binary, the text size actually shrank by over 40,000 bytes. Across the board, fewer instructions are executed during compilation. It's just a massive, tangible win for efficiency.
And here's where it gets really interesting. You'd probably assume the big industry standard libraries have this all figured out, right? Actually, no. Massive standards like libc++ and libstd++ still have sluggish pushback operations because they need a stack frame for their fast path. libstd++ is notoriously heavy. It inlines the whole reallocation process, forcing 6 calls saved registers right onto the fast path. Even highly optimized libraries from Boost and Google do the exact same thing. Thanks to this tail call trick, LLVM's small vector basically stands alone with a truly fixed, frame-free fast path.
But there is a catch. Chapter 5, the final trade-off.
Like everything in computer science, there's no free lunch. The tail call trick is genius, but it's not a silver bullet. For a single isolated pushback, it absolutely wins. Zero stack frame overhead. But what if you put that pushback inside a loop?
Well, suddenly the script flips. Because small vector passed its address to an out-of-line helper function, the compiler gets paranoid. It assumes that helper might have changed the vector's size, so on every single loop iteration, it has to painfully reload the metadata from memory. Meanwhile, good old std vector inlined its slow path. The compiler knows exactly what's up, so it happily keeps all that metadata in the super-fast hardware registers. Inside a loop, the bloated std vector actually beats the newly optimized small vector.
Which leaves us with a really fascinating question. In systems engineering, are you optimizing for the single action or the endless loop? To keep that metadata in registers during a loop, you have to catch the return value from the slow path without escaping the object. But if you do that, boom, the heavy stack frame you just got rid of comes rushing right back. It's the perfect mirror of trade-offs. You can have a frame-free single operation, or you can have register-perfect loops, but you definitely can't have both. Understanding these invisible mechanics completely changes how you look at code. Next time you type pushback, maybe ask yourself, what is my compiler really doing behind the scenes?